Okay, good morning and welcome to the Introduction to Arena-flow by CPFD Software webinar. My name is Niraj Mehta, Solutions Engineer here at CPFD Software, and I'm excited to be your host. Arena-flow is our advanced simulation tool for sand core, mold, blowing, shooting, and curing, and we're thrilled to be able to demonstrate it here for you today. Today's webinar will include an introduction to CPFD and Arena-flow. Arena-flow is trusted by OEMs, foundries, equipment manufacturers, and core and pattern shops that complement metal flow and solidification tools, helping ensure cores that are right the first time. The webinar will include simulated core making processes, including cold box, shell, inorganics, green sand molds, and more. We'll talk about what makes Arena-flow unique. It's an air-driven discrete particle method based on the MP-PIC method by CPFD Software. We'll talk about considerations prior to launching a core blowing project, and we'll have a live step-by-step demonstration, including post-processing with the bundled Tecplot 360 post-processor. Finally, the webinar will conclude with a Q&A session with CPFD engineers. This webinar will be recorded. It'll be sent to all attendees and registrants, but it'll also be available on our website or on our YouTube. If you have any questions throughout the webinar, please ask them using the provided GoToWebinar panel, as you can see on the graphic on screen. You don't have to wait till the end of the webinar. If you think of a question, ask it immediately, and we will queue it, and then we'll be able to answer them at the end of the webinar. And if we don't get to your question, don't worry, we will make sure to follow up with you afterwards. And now for our two panelists. Peter Blazer started with CPFD's Arena-flow affiliate in 2003 as a senior CFD engineer before being promoted to Arena-flow product manager in 2006. He simulated hundreds of cores and molds and was the original designer of Arena-flow's foundry-specific interface. Today, Peter Blazer is vice president of CPFD Software, the responsibility for both Arena-flow and Barracuda Virtual Reactor business units. Thomas Brandt joined CPFD and Arena-flow in March as manager of foundry products and services. Thomas has worked with pattern and core box modeling and simulation software for over 30 years, and he supported the global foundry industry by using Arena-flow since 2005. And with that, I think I'll hand it off to you, Peter.
Well, thank you. Thank you, Niraj. Everybody, I'm going to give a quick overview of our company and product, and then Thomas is going to get to the demo. And I will just say it's really good to get back to the Arena-flow roots here. Here's our company, CPFD Software. We are advancing multi-phase simulation and technology, and we've been doing this via specialized software for gas particle systems since 2003. We do have two software products. The first and the topic of this webinar is Arena-flow. Arena-flow is foundry-specific software for sand cores and molds. We also have a product called Barracuda Virtual Reactor, and really that's the general purpose product for broad applications across the fluid particle space. These could be fluidized bed reactors for gas solid, liquid solid systems, three-phase systems. And Barracuda Virtual Reactor models the three-dimensional transient hydrodynamics, the multi-phase hydrodynamics, the heat transfer, and multi-phase reactions in industrial scale units. But let's be talking about Arena-flow today. So what's Arena-flow? Well, Arena-flow, our Arena-flow business unit is software and related services for sand cores and molds that ultimately results in tooling that's right the first time. It takes that trial and error process and moves it to the computer via virtual testing. And this is particularly important now to able to capture and retain core making knowledge, especially as the people with deep experience in this area are retiring. Ultimately, using Arena-flow, we're talking the Arena-flow product. What it does is it really lets you understand and eliminate scrap. First, understand, why is sand moving in an area? Why is it not moving? Why is the curing front doing something surprising? And once it's understood, you can work to eliminate that scrap, and often and very quickly with one or two iterations. As a result, cores and molds made with Arena-flow have optimized cycle times, You can minimize the dosage, increase uptime, extend tool life, run at lower pressures. And ultimately, it's about reducing costs, whether that's capital costs, operational costs, energy savings, all achievable and regularly achieved by our clients using Arena-flow. So let me talk to a few different application areas. So the main area, and we're going to demo this today, is blowing and shooting of cores. So Arena-flow is modeling the motion of the sand in the tooling, how it compacts, how the speed of the sand during compaction is influencing areas that are first to fill, last to fill, how well they fill, and even resulting in then subtle differences. So what is the final density when filled? And so we're going to demonstrate that primarily today. But there are modules also for other processes. So curing of cold box cores, be it amine, SO2, looking at how the curing front moves through the core. In this case, you're looking at the areas that are last to cure. These are the ones that are keeping, could be uncured. Typically, they're resulting in extended cycle times. As this loops again, you're going to see areas that are first to cure. So areas that bypass the drag side very quickly. This is where you're using excess consumables. And so really looking for that optimized cure. For inorganics, a few years ago, we added modules for inorganic heating and dehydration. So looking at the heating of the core from the tooling, from the hot air passing through, and then looking at that, the effect of that on the moisture, the residual moisture in the core as it's being vaporized and driven out, the vapor in the gas phase, and then overall times on the cycle to avoid the overdrying. And while a lot of what we'll show on this particular webinar is individual cores, these cores hang under magazines, whether it's a single core, multiple cores, or a family box. And so Arena-flow is used for that, especially for large cores, cores that might require double blow or might not have sufficient sand in the magazine. Arena-flow is a powerful tool for that. And while we'll demonstrate the cold box process today, please know Arena-flow has been used for many different processes, including cold box. I remember doing some of my first shell sand molds in 2004, I think it was. So shell sand, more recently for inorganics. For some of those, we have the curing modules as well. You have sands with different flowability, and even green sand, the filling of the molds. Arena-flow has been able to predict areas that are difficult to fill and why and what to do about it. Briefly, here's a demo, and this is a video from GIFA over a decade ago, but with a head water jacket core that has all the tubes in an integrated blueprint. And Arena-flow is used to simulate the flow of the sand and how it's influenced by the air as it escapes through discrete vents. And so looking at the results, we see how Arena-flow is predicting the filling of the sand, and not just the view as what the sand would be colored as, but the last to fill regions compacted by volume fraction, and then really what's happening in these regions. Why some are being filled with fast moving sand there near the tubes, should be fine. In other areas where it's slow moving sand, where you're going to have variability and ultimately leading to the potential for defects. And so once you have this idea of where these defects could be with virtual testing, you can change venting, change tubes, explore process conditions, and optimize your cores and molds. Before we get over to Thomas, just real briefly, a few things that are unique about Arena-flow for sand cores and molds. We don't try to do everything. We're not metal flow and solidification software. We complement that. And here's a few things of what we do uniquely for sand cores and molds. And the first is discrete sand particle properties. So each particle in Arena-flow is a discrete Lagrangian particle for the CFD types out there. That means every particle has its own size. You're capturing the sand, the size distribution, typically from a sieve analysis, the density, the type of sand, zircon, silicon, something manufactured, and the properties of that sand, and that's a direct input into the software and significantly influence the Arena-flow results. And then this is just cool. The software works by air-driven sand motion. So what you're looking at here are the particles, the sand, colored by the speed. So high speed stuff's sand moving is in red. As it compacts, it turns blue, it stops. And then those vectors, those arrows coming out of some vents at the end, and this is just simple test core blowing uphill. But what you see is that when there's little sand in there, that air is just screaming. It's screaming out those vents, and it's pulling the sand, and the sand's moving very quickly. But as those vents start to get covered with sand, now the airflow decreases, and you have less airflow to move that sand, and the sand starts moving more slowly. And this is really the heart, and while it's easily to visualize, this is really the heart of Arena-flow. And while it's easy to visualize on a simple core like this is really what's happening inside a lot of the complex geometry, and we're able to compute that. Also, this is what we do. We aim to model sand cores and molds and do it really well, and we've been doing it for a long time. So there's decades of experience with the team. I look back to the 2003 paper by our founders, Ken Williams, Dale Snyder, and some folks over at General Motors, Mike Walker, Sheila Pocheski, ended up winning this was a paper called Process Modeling Sand Core Blowing. Ended up winning the Howard F. Taylor Award from the AFS for best paper, most significant impact, long-term impact expected from in the industry, metal casting industry. Found some old photos from training classes out in Albuquerque, on-site at customers, working with some customers in Japan, 2004 to 2006. We were honored again in 2010. DJ and I were there representing the teams where we won the AFS Applied Research Award with Arena-flow and General Motors. And then even Thomas, while he's new to our company, he comes with 20 years experience using Arena-flow and over a decade before that of CAD and pattern making and core design. So this is what we do, and we're here to help. The software also does come with powerful and extensible post-processing. I say powerful. Thomas will demonstrate that and look at how the cores, different views of cores, different parts of post-processing. This is all native within the Tecplot that comes with Arena-flow. I say it's extensible in that there are a few CFD types here on this call, and you can dump raw data and torture it however you want and do additional analysis. And this is really how we partner with others and get new modules in place as well. And that's all possible to do with Arena-flow. And then beyond that, we're partnered, whether it's on the compute side, on the post-processing with Tecplot, with cloud providers, and then in the industry as well. Just in the last few months, there's been some news and announcements, and check those out on our website. Laura Mendy and Arnac over in Spain, some news about what they are doing with Arena-flow. Lempi Reich's a great partner of ours here in North America, benefiting them and their customers. So we are open to partnering with others as well. And lastly, world-class support. It's always weird for us to be the ones saying that. Let me just say, if you're using Arena-flow, you're getting support from humans. You can talk to us. We will help you, and those humans know what they're doing. So we're here for your success. So that's really the intro on my end. At this point, I'm going to turn it over to Thomas, and he's going to do two things. He's going to tell you first what's needed for an Arena-flow simulation, whether we're doing that through services or you're using it yourself with software licensing, and then he's going to do a live demo. So Thomas, tell us about Arena-flow.
Thank you, Peter. Yeah, let me try and go ahead and explain what we need. So on this slide, we need a model, right? So what's of interest to us? Any surface that has contact with air and sand. So we want the internal geometry, like the core itself, internal blow tubes, and something that either represents a blowhead magazine, if we do a full box, or plenum that we can use for an indefinite sand supply when validating an initial single cavity layout. Now the second thing we need is any air escape, so vents, ejectors, parting line vents, anywhere where air can exhaust. Now, we can provide locations. If we do a design from scratch, we're happy to do that. And then, if you've got a baseline, then we need the information from you as we're working on your process. As Peter mentioned, we need the sand data. So any sand analysis we need, as well as an understanding of the grain shape and binder content, as this will impact flowability. And we can use any sand data, any pre-made sand, any ceramics, additives, sand mixes, zircon, silica, whichever. We can run those as a separate or combined mixes, as long as we got particle distribution and specific density data. We are happy to model those, and they can all be implemented into Arena-flow. Last but not least, we would like to know, what kind of process you want to simulate. It's cold box, warm box, hot box, green sand, inorganic, as mentioned prior by both Peter and Niraj. We need to know, binder again, it's viable for flowability. If we're doing green sand, bentonite and moisture contents as well, for moisture content for dehydration in the inorganic process. Flow pressure and time. Again, if we do a baseline or process audit, we want to take your data. If it's a new design, we can certainly give advice on those once we have an understanding of process and the machine that you want to run this tool on, blow that core on. Same goes for gas and purge. We have certainly values we can apply, but again, if it's a baseline, we want to have as accurate input as possible, and we would apply your process data. So let me go ahead and start sharing my screen. So what I'm going to do here is basically go through a couple of setups, and as well as having them pre-run. So we have our main GUI of Arena-flow. We got 4 modules, one for binder coated sand, which is also defined like green sand, shell sand, any process that involves temperature, so shell, warm box, hot box, with regards to blowing, inorganic curing, the newly developed module that is specific for dehydration, and last we got gas curing, which is steady state, and transient curing for cold box, as Peter showed you a couple of videos for earlier. Today I will run a binder coated setup. So I'm going to start that, maximize the screen. It is already present, so I'll just double click on that to open the project. Now, step 1 would be to generate a grid or mesh that we can actually run the presentation on. So simulation on, so I'm going to click grid generation. I've imported them as individual files. It makes post-processing a little easier, but you can certainly just combine all files into one if you so desire. I added a couple of lines to make sure that I got a nice and clean interface between flow tubes and core cavity, as well on the steps to avoid kind of any unwanted chamfers or stemming from the grid generated. Once the grid is generated, we do have several options: view grid, view CAD, view transparent, and compare grid. These can all be opened individually. It will automatically start Tecplot, and from the Tecplot menu you can select them. What I'm going to do is I'm going to open up Tecplot, and as you see, I got all 4 grid views on one layout. This is all user data. It's a user-defined layout which you can create once you have Arena-flow and Tecplot. So zoom in, they follow along simultaneously. I can use any of the preset views just to check that we got good and nice open connections between blow tube and core. Looking from the side view, see we got our nice clean interfaces. Just as a reference, we got the CAD as well. And then lastly, we can actually see an overlay of the grid and the mesh and see how well they actually align. There's a little view here, but it's difficult to get it with a resolution that isn't gonna kill the simulation due to the draft on the core. So once I'm happy with that, I'm going to go back into Arena-flow, go to the next step, which is define the orientation of gravity. Now, as my CAD is aligned with that, I'm going to select -C. Send type. Again, I am using predefined data. I have my screen distribution here, 1 material. Now we got % retained and grain size and specific gravity. So that's our input. Send location. We need to tell the software where is the sand located initially prior to starting the transient process of blowing the core. Blow pressure. In this case, I've actually chosen to create a pressure profile which extends way beyond what I'm going to use for the actual blow time, but it's just a heads up. I could also, and typically will use for blow, a constant pressure. And when it's a single cavity, we account for the pressure loss in the sand column and typically deduct 20% prior to running the simulation. So we're not using the actual on-machine pressure, but we are reducing the pressure to account for the pressure loss. Vents definition. I do have predefined vent locations, sizes, and open area. I've done all of this in CAD. We do have a interface template that allows us to transfer CAD locations into a vent table that Arena-flow will read. It is a lot faster, a lot easier. You do not have to do any typing, and you also kind of ensure that what you have on the CAD model, should you want to send that to a pattern maker or you manufacture the tooling in-house, you got data that ties together with what you're doing in Arena-flow. Time control. Now this is the anticipated blow time on the machine. So typically does not make sense to go less than 1 second. So I prefer to set realistic on-machine settings. So 1 second, I believe this core will fill in 1 second or less. Models, we have various models that we can look at. We can look at tool wear, wipe off, flowability. This is where we account for grain shape and binder and fill settings. In this case, I'm just going to open up Viva. It's the default is 2%, which is commonly a little bit high. So I'm going to change it to 1.2% instead. Click apply. Data output. We got a range of standard outputs, and then we got the option to say, okay, if we're using like an additive or a mix of silicon zircon, it might make sense to add, particle material density, or looking at segregation, and it might be valuable to add particle radius. We can just turn them on, turn them off if we like, without any significant impact to runtime. Transient data. So they are similar to control points in a casting solidification software. These are control points or transient data points that will record local pressure, any local velocity with regards to dehydration, air temperature, water content, etc. I'm not going to apply any, but it's definitely a good option. Flux planes. I have those predefined. I would not run a simulation without any flux planes. If we've got a multitude of flow tubes, maybe consider grouping them a little bit, but so I don't have to add 500 flux planes. But in this case, I have 6 blow tubes, so I'm adding a flux plane to each individual blow tube. What is the benefit of adding a blow tube? It will record volume flow, airflow, and add the ability for us to color the sand by which blow tube. So we can actually trace by color the sand back to a blow tube, similar to casting solidification software, where you can actually trace the metal by ingates. So that's pretty helpful. Now go to run. The first step would be to run solver setup, allowing me to check the setup, and then similar to grid, we can click on these 4 results. Again, what I'm going to do is I'm going to load a predefined layout. So allowing me to visualize the 4 setup, check outputs, got my boundary conditions, so my blow pressure defined, and any air escape boundary conditions. On the core, got my sand location. Want to check that we do not have any sand in the actual core cavity, but I did bring the sand almost down to the core. Check flux planes. We got flux plane on each tube, and the location of flux plane aligns with the sand data, so we have no gap in time steps. And then last but not least, we got our venting, carbon drag ejectors. They are all green, which indicates that they are well applied and surface contact is good. So once I'm happy with the setup and validate everything, so it appears to be okay, go ahead and run solver. Now, as I mentioned earlier, I've done that. So again, I'm just open Tecplot and allow me to open a layout for the first setup, the first version. Again, while we have all the individual results here, I made a combination of 4 output that I like to use. So we got sand ratio, we got particle speed limited, so any sand that moves with a speed of less than 0.2 meters per second has been blanked, as they do not, particles moving at that speed or below do not contribute to any further compaction or increase in density. So what we see is when it's transparent, it's resting particles and compacted. Core density, shown this as iso surfaces. So when we see blue, it's typically not good. And then we got pressure. We just run that a little further along. Just see how we can simulate that on screen as a process steps through time. We also have the ability to output videos or images or sequence of images for, for any kind of report generation. I'm not going to overwrite that, but we can create videos or individual outputs, individual screenshots, any typical file format for single images. Another result is that I would like to show is the colored sand and the flux planes. So the benefit of that. This would be common outputs. Again, looking at the volume. So what I did, I created user results. So this is the total mass of sand through all 6 blow tubes. I'm not looking at the individual performance in this case, just looking at the overall performance. Got a estimated fill time of about 0.3 seconds. And then we got our moving timeline. What we see here is we got a fairly soft bend, which indicates a slow filling towards the end. We got some particle movement as we see predicted wipe-off, resin wipe-off, indicating the actual volume of resin that would stick on the surface, as well as tool wear. Now we only see tool wear in the blow tubes, which is a good thing. We'll always see some wear in the blow tubes given the particles and the turbulent, normally fairly turbulent behavior in a blow tube. High speed. So that was kind of the first setup. So what did we learn? Well, we got something that we could possibly improve. Looks like we got maybe some soft areas from before when we looked at the other layout. See that we got soft areas here, indicated here by the yellow. Again, here you can see clearly a correlation between density and volume fraction. So how to address that? Well, let's create a new case. So file, literally just create a new version. to maintain all data. Quickly open that version. Now the only thing I want to change is the vents. So I have another predefined vent table I'm going to load. With the changes. They're not visual until I run solver setup. So I'm going to go ahead and run solver setup to be able to visualize my vents. Okay. So let's jump into the pre-run version of that setup. File, load Arena-flow. And again, I do have the same layouts as before for the initial baseline version. So are we noticing anything here that is minus? Well, look at time step. When we start to it from 0.1 of a second, recall how the other one behaved. We're now starting to see it filling a lot faster. And let me load the other layout that we had before. And one thing we notice now is we see that curve. It has an almost 90-degree bend, which is really great. Means that once we actually stop filling, we do not spend time on filling a small volume. With another thing is that we see we got a estimated fill time of close to 0.2 seconds, which again adds to the process robustness, meaning that we have more time to encounter vents being a little clogged, maybe some air escaping in the parting line or loss of pressure, and we should still, within the 1 second, have enough time to overcome a lot of those issues and then still produce cores until we end up with the tool being too dirty or some machine issue with potential pressure loss or whatever. So how do they compare? Well, let's take a look at that. Again, using some pre-prepared layouts. We've got baseline version, taking a look at the volume fraction or percent ratio and speed. Clearly, we can see how version 1 is going to overtake the baseline and fill in significantly faster. How does that relate to the density? Well, let's load another layout. And in this case, I've applied, you see the white circle, I'd applied a point by just clicking a location that would be similar to a transient point. So individual curves, again, over time. And then finally, we got an overlay of the two curves, and we can see how unstable, not very good flow. We see, increase in density, then we drop off as particles probably shift around, move around, drop down, then they start to build up again. But we see the common picture of once they reach a final compaction, then start to move again, they will drop down in density or compaction. Not a very nice behavior. We do see for version 1, it does build up very quickly and stays stagnant, there's no movement, it just constantly increases, and then we have a filled cavity. Again, we can compare the flux data, the overall fill, a little bit more, looking at send ratios, resin wipe off. We see still something that needs to be addressed, but significantly less resin wipe off. We do see the two curves on top of each other overlaid, and we see clearly how version 1 has a much better fill pattern. And again, this is all done, trial and error on the screen. We're not cutting any chips. We're not spending time, worst case scenario, with sending the tool to an outside tool manufacturer and having done stuff. We're all doing this in a virtual world and on a reasonable computer. This is overnight work, running 3 or 4 versions of this, set them up, queue them, run them overnight, and when you come back next morning, you have time to look at the results. So what did I change? This is the baseline where we got our cope, vents, and blow tube. Added a significant number of vents to the interior, but cope vents only, as indicated by the green. And then, added, for the sake of it, added a few parting line vents to each hole. And with that, that concludes my presentation, and I will turn you back over to Peter and Neeraj. Thank you.
Thank you, Thomas. And let me just get the screen control back. Just a moment. All right. So with that, Neeraj, you want to take us into the, tell us a little bit about how to get started and lead us into the questions.
Sure, I'll give Thomas a chance to get a glass of water. Yeah, so let me talk about our various offerings. So primarily, when we deliver the software, it is through a software licensing model. This would be a user at your company running the software and purchasing a license from us. This is our most common way of delivering and deploying our software. We're very flexible with how we can deliver software, both on-prem and on the cloud. And in terms of operating systems, it runs on Windows and most Linux distributions. We also offer other ways of accessing the Arena-flow technology. One is through our engineering services. So this would be your engineers partnering with our engineers to work jointly. Often we'd be running the simulations, and this can be in the design phase or in the troubleshooting phase. We also offer maybe hybrid programs. Well, there's a program we like to call the Quick Start program, in which we would set up the first model, calibrate it, and train up your engineers in a custom training scenario, and then deliver that calibrated model to your trained engineers, who would be able to then take it and use it as they see fit. And again, we are a small company and we know our customer base very well and we work with them very tightly. So we are very open to custom kind of collaborations, spanning basic training scenarios, group training, and various different other forms of technology transfer and software delivery / services projects. And finally, we also do work in R&D and we do work with industrial partners. If you are interested in trying the software, we offer training classes, which would be a great way to not just have a hands-on demonstration of the software, but also be able to interact with our engineers, ask them questions about your own specific system, ask them considerations or various questions that may come up that you can only ever really ask once you start using the software yourself. So we offer web-based training, but also we have the capacity for on-site training. We're also happy to set up a software demonstration. Again, this can be web-based or in person, and this could be with your own data. This could be with maybe some of our preset models, but please reach out to us at info@cpfdsoftware.com if you're interested in learning more about our various offerings or about trainings or demos. And with that, we will get into the questions. I see we have a lot of questions from our audience here. I'm going to maybe pick some of these randomly, and we'll go from there. Our first question says here, how important is mesh size to accuracy of results?
Yeah, I might speak to this one. You know, I come from a CFD background, general purpose modeling, and I'm to this day surprised how insensitive Arena-flow is to mesh size. Now, let me put a caveat on that. You need enough mesh to capture what's the basic physics of what's happening. You know, typically that's multiple cells across a blow tube, spanning an area with a defect. If there's a recirculation pattern that's slow to pull air back uphill, you need enough to capture those physics. But because Arena-flow handles the sand separate from the air, so it's not one Eulerian phase for the CFD folks. It's the particles are discrete, gridless. We use far coarser grids than you would use for most computational fluid dynamics, and as a result are able to capture things with far less mesh sensitivity. And this is something that we can work with you on, especially during a training, initial project or quick start, where Thomas can work with you or our team and run that grid sensitivity study like you would do. But it's surprisingly not terribly sensitive.
Great. We have another question here asking is there any difference between the Windows and Linux versions of Arena-flow?
Thomas, how are we going to do this? You want to answer it? Should I?
Yeah, let me do that. So in the past, we know everybody was definitely running Linux for stability issues. Windows had it quirks. Today, I will say that there is really no difference between either platform, especially now with Tecplot, which just runs great, runs very well on Windows as well. So yeah, I would say whichever platform works best within your organization, you can safely run on that. Works just great.
Awesome. Next, we have a question here asking, first stating that they really like the version compare, and then asking, is this version compare limited to only 2 data sets, or can it do multiples?
So let me answer that. No, there's no limitations. The only limitation is the size of the window. So you imagine you have 10 versions, then you would have 10 small frames in the layout. So you might have a little bit of loss of detail just purely based on size, but no, there's no limitations other than the level of detail that you would expect. So a physical screen size would be the limitation, not number of versions.
And I think this question came during the demonstration, but what core machine is this? The person asks, I've never seen a box over every tube before.
Want me to reply to that, Peter?
Sure.
Okay. Yep, that is a good question. No, you have not seen and this is not machine specific. This is specific to running a single cavity initial study. Before we move on to any machine, we want to make sure that the cavity fills, and we got a robust venting and blow tube layout for that single cavity. That helps to remove any kind of unknowns. When we do a full magazine simulation, we know that the cavity fills, so we're not concerned about if we see an issue coming from the blow of the full magazine. We know that is an issue with the actual transport from the magazine into the cavity. So initially, we just want plenums where we can define an indefinite send supply, and just to minimize runtime, take out dead particle space. That's why I chose to put, in this case, a small rectangle on top of each blow tube.
Related to that, Neeraj, there's this question on, where is it? Really large cores. Why don't we do that one next?
Yes. So the question asks, have you any experience in prediction for a double blow for really large cold box cores?
Yeah, no, that's the one. That's one I saw. Sorry, Thomas, you want to go, and I'll add to it because I have some too.
Yeah. So that's a great question. Typically, the only reason we would apply a double blow is because of lack of volume in the head. And in that case, we're actually working on a new feature which will allow us to do true double blow. So we will base the second blow will be based on the particle location from the first blow. This is going to be huge. So yeah, I mean, we've done it in the past, but it has been manually applying, send locations from the first blow. It's definitely possible. And if Peter has anything to add, I'm going to leave.
Yeah, you hit it. I mean, stay tuned. We have Arena-flow 12 coming out later at the end of the summer, and that has ability to initialize core from details from another simulation. So that's going to make it not a manual process anymore.
Great. And I think there was a follow-up question to that question about really large cores, which is, what are the typical times to set up, solve, and look at results for a core, and how much of that solution time is dependent on size and complexity?
Peter, you want me to answer that?
Sure.
Okay. So runtime is mesh size, number of particles, and geometry dependent. If we're talking about a very large, maybe like an engine block core, I've seen runtimes of maybe a week, and in this case we're talking about a mesh of like 5 million, a decent particle cloud size of probably 25, and estimated core weight, between 300 and 400 pounds. So let's say a week runtime, setup, once you have a good mesh, which is, I look at it 3 ways, you got the mesh, which is, take some time, depending on experience, maybe 1 to 2 hours, and then the addition of venting and blow tubes. If you do it based on the CAD, It's very straightforward. I would set about 1 hour again. So with a large job, you set it up within 3-4 hours. So half a day, you are ready to run. With regards to post processing, I would always advise, look at results while the simulation is running. Look at the progress. It doesn't necessarily make sense to run the simulation for 1, 2, 3, 4, 5 seconds if the cavity is actually full or there's an issue. You might want to move on. And then, time to post processing. You can do a lot of layouts, and having predefined layouts helps. But setting it up, if you set off a day for generating results and generating reports, I think you're within a very reasonable time frame.
Fantastic. I think we have only 4 more minutes here, so
Well,
I think. Oh, sorry.
Well, again, let me just add on that. I think, Thomas, you kind of were assuming the question's asking like how long could it take in terms of an extremely large model. So that 5 million cell model you mentioned probably has 75 million, 100 million, or over 100 million computational sand grains in it. But a typical one, like the one that we looked here, some of those simpler cores, I think last time we chatted, you typically can run those, several of them overnight. So hours for a blowing and literally minutes for a curing simulation. Is that correct? And can you speak to more typical?
Yeah, and that's like I mentioned during the demonstration. Typical ordinary, not necessarily ordinary cores, but if you look within the broader perspective of the cores, you get very, very far within an overnight. You have at least one version. Turnaround, I'll say a normal turnaround is between 1 and 2 days.
Yeah, no, thanks for that. And I needed to step in there because I don't get to run the software every day anymore. So my experience is a little dated.
Yep. Oh, I much appreciate someone translating my word mumbling.
No, that's great. Go ahead.
We have about 2 minutes to the top hour here, so maybe one last question and we'll wrap up, and then we'll follow up with these other individual questions with people via email. We have 2 questions here that seem to be on a fairly similar topic. One is asking if Arena-flow can handle sand mixtures, and maybe a more in-depth question asking us to address mixed density sand and avoiding segregation in blown cores, as it says is often the case.
Yeah, no, absolutely. As long as we got I prefer to have an as accurate as we can get it description of particle distribution, screens, and material density of any particle group or material that is involved in your process. We can model it. Also, if it's a mix of various densities, we have very good results, very good relation between, potentially even looking at adding anti-segregation measures in your system. We can look at any part of your system, sand supply, whichever that involves air-driven particle motion. So yeah, I've not seen a mixture that we could not yet find a way to simulate, as long as we got good data. If for some reason there are elements that are missing, we have enough knowledge to create some baseline sets, but again, accurate data is definitely preferred. With accurate data, you get accurate results, and that helps us to achieve what we're striving for, that you get it right the first time.
Fantastic. And that brings us to the top of the hour. So we'd like to conclude the webinar. We thank everyone for attending and for asking wonderful questions, and we hope to be in contact with everyone soon. Once again, thank you for attending our Introduction to Arena-flow by CPFD Software webinar.